Hello, everyone. I'm Dinesh, and I'm really excited to be talking to you all. So I'll kind of like Mayur introduced, I'll start by speaking a little bit about the work that we do in my group, which I call the Perception Action Learning Group. We focus on perception through action and for action, and what that means that will become clearer soon. And then I'll quickly overview some of the work of my colleagues who are also working on similar topics here at CIS. So so many of us working with robots would really like to build general purpose robots. And in our group, we focus on visually enabled general purpose robots. The reason we do this is because if you take a look at what robotics has been able to accomplish for us, it's a little bit disappointing in the sense that it doesn't really live up to the promises that science fiction has made, 100 years ago now. And really, robots at this point are only working primarily bringing value to us in sort of controlled factory automation settings, and not really enabling sort of increased value in our homes, offices, hospitals, and workplaces, et cetera, to the extent that we would like, right? And so the way we think about this in our group is that uh, the main difference between these two settings is that on the one hand, you have sort of fully observed and well-modeled setups, and on the other, you have sort of many unknowns and uncertainties. And this is where perception becomes really important, because really high bandwidth perception corresponds to extracting information about the environment and resolving all these various uncertainties that exist in these other environments that we'd like to get robots to work in. And so high bandwidth perception, like vision, is really key to this, because vision is able to extract a lot of information in every frame, right? And so a big lens through which I view my research is to think of action as both a means to perception and an end for perception. And what that means is so kind of embodied through these different projects. For example, we can use perception to improve action by using model-based reinforcement learning, where you're modeling the evolution of a visual state over time. And I'll talk about that a little bit. But then we also have work, for example, in object-based representations that enable faster control, or in real-time perception for agile control. If you want to drive a drone, for example, through a really fast, in a really fast maze, for example. And we have work in tactile perception that enables contact-rich manipulation. On the other side, how does action help influence perception is perhaps a little bit newer to several of you. But there is this idea of active perception, where you can actively move your sensors about in the environment to gather data. And that helps you improve your ability to perceive the world. And I'll touch on that in one of the next slides. But we've recently also worked on other topics like causal inference through experimentation, action supervised representations for images, and so on and so forth. Right? And I won't have a chance to touch on all of this, but I just wanted to quickly give you an overview. Right? Okay, so coming to the first thing that I wanted to highlight, we've been working for a long time on visual dynamics models. How do we get robots to predict what the future state of the world is going to look like visually based on their actions, right? Now, this is a really hard problem, because predicting what a future image is going to look like is a really high dimensional problem. And so the way I think about this is that we need to somehow abstract this problem out to make it lower dimensional in some sense. And one way that we've made it lower dimensional is by abstracting it out in time, so that rather than predicting all future time instance, instead we kind of predict some important key instance. So for example, between this image of the robot over here and between this image that we'd like to get to, with the robot having pushed this object to the left a little bit, there is this middle image that we would like to be able to predict at which point the robot has to actually make contact with that object that it's trying to push. And we do actually predict it using some methods, right? And so we've developed methods that are capable of making such predictions and then kind of decomposing a long task into a series of subtasks, and thus making the problem of learning how to solve complex tasks easier. And so we've worked on some extensions to that also make it possible to do this kind of hierarchically. Okay. Another way that you can abstract this visual dynamics learning problem is by saying, I don't want to predict the state of my world is not really the set of all the pixels in it. Instead, it really is the set of just the objects in it, or just the key points of a robot in it. And as long as you're able to get those little bits right, you can actually get most of the information about the world right. And so we've developed methods that are able to abstract out the state of the world, the visual state of the world, into a set of key points. Like, for example, in this case, you'll see a particular key point that's marked in sort of cyan here. That's the key point that we're actually identifying as the one key point that we're going to do control with. Or in this case, we're developing sort of neural key point based methods. All of these are neural key points on the robot that sum up the full state of the robot, the full pose of the robot, without having access to any proprioception on the robot. And here is an example where we've done similar things, this time not modeling the robot, but instead modeling the rest of the world aside from the robot. So how do we get to represent an object in the world and then use that for performing tasks? So we can do cool things like, for example, tracking a human demonstration and then repeating that human demonstration with a robot, because the human demonstration is abstracted out into just a set of key points on the object that needs to be moved, for example. Okay, so the next kind of maybe key thing that I want to highlight is work on the other direction of the arrow. How can action help perception, right? So how can you move in order to see better? And so here is an example of an illustration of this, where you have a robot, you'll see it soon, a robot that's kind of moving an object about in its hand. And as it moves, its impression of what category that object belongs to improves, and it actually finally gets it right after moving it around in the appropriate way. And you can do this in other settings as well. Perhaps you have a robot in a particular scene that has to kind of move its camera around the scene to recognize which category the scene is. Right? You can do these things also with things other than vision. So you can use, for example, touch. And so we've done some work with touch sensors that lets a robot recognize which grasps on a particular object are likely to succeed. And so it adjusts its grasp so that it moves to more promising grasps after sensing it first. Right? Okay, so I will, in the interest of time, I'll quickly move on to the next slide, where I wanted to show some of the students we have. This is a slightly outdated picture from a few months ago now. So I have started at Penn in the last year. So all of my group pictures are unfortunately these Zoom pictures, but hopefully by the time you all are thinking, we'll be back on campus. There are other vision faculty on campus, of course, including extremely senior faculty like Costas Delinides, who's made some contributions all across vision and robotics. John Boshi, who works on core vision problems with cool application areas, including, for example, medicine. CJ Taylor, who works in 3D vision and its applications in robotics. And Mark Yatskar is one of our new faculty who works at the intersections of vision and language. So we really have connections between computer vision and all these areas, including robotics and language. And of course, machine learning is integral to a lot of the work that we do here at CIS. We also have other faculty collaborators within CIS, including Osbert Bastani, who works on systems and ML, Nikolai Matny, who works on control theory and ML. So some connections you might not think of as being immediately obvious, but really we have a really collaborative department and a collaborative environment here at Penn that enables these kind of cross-platform, cross-departmental collaborations. So Michael Poza and Vijay Kumar are some other collaborators that some of my students are working with now too. Okay. With that, if you have any questions, feel free to send me an email, look me up on the Penn CIS webpage, and I'll hand it off to the next speaker.